property associated with the continuous time and discrete time systems is the invertibility. Okay, or if the system is invertible, we say that these systems are inverse systems, so that the inverse exists. Okay, so a system is said to be invertible if the distinct input leads to distinct outputs. Now there is an illustration in figure 145a of the course text, and it says that for a discrete time case, if you have a discrete time system, the system is invertible. If the system is invertible, then an inverse system exists that, when cascaded with the original system, will yield an output W of n, which is equal to the input X of n to the first system. So you see in this figure 145a, this is your figure 145a, you are applying an input to the system. This is a discrete time system which is handling a discrete time sequence X of n. The output is Y of n. Okay, the first system is Y of n. Now if the system is invertible, then there must be an inverse system that exists. Okay, so this inverse system is associated with this system, and what it does is, whatever the system do, or the operations or the transformation that it performs on the input sequence to produce an output sequence Y of n, it's reversed by the inverse system, so that the output of this cascaded inverse system will yield an output that is the original sequence X of n. Okay, so for example, suppose you have a continuous time system, this is CT, and you have a continuous time signal X of t. So the first system, what it does is simply scales the amplitude of the signal xt by twice. Okay, so y of t is twice xt. A very simple inverse that exists is providing a factor or a multiplication factor of half with y of t will yield another signal w of t, which is exactly equal to xt. Okay, so the inverse of the system exists. Similarly, if you consider an example of discrete time system which we have discussed earlier for an accumulator system. Okay, this is an accumulator system. So what it's doing is, it's summing up. It's doing a running sum on all the samples of the input sequence X of n, that is from x minus infinity to the present time index n. Okay, so the system might have some registers that has stored the values of the past samples of the input sequence X of n. So it is summing up from x minus infinity to all the way to xn minus 1 to X of n to produce an output sequence Y of n. Okay, now this you understand that we can write this expression as you've seen earlier. I mean, you can bifurcate this into two terms. So this is from k equal to minus infinity, and if the upper limit is up until n minus 1, and this, since the index is over k, summation index is over k, you still retain that the argument is over k, and then the only thing that is left is X of n. Okay, so this is an alternate description of this accumulator system, and that is equal to Y of n. So we're right here. Okay, we are just in the accumulator system. This is an accumulator system. Okay, this is an accumulator system. We are not talking about its inverse right now. So this expression, you can see, can be written as Y of n minus 1. Okay, it means that whatever samples that we had preceding X of n, okay, that has been accumulated, and the output was up until n minus 1. So the output, in order to have the output Y of n, we need all the summation of the samples up until n minus 1, and then if you add to it the present sample index n, you get the Y of n. Okay, so this is an alternate difference equation that describes the same system accumulator. And if you take the difference of y of n minus y of n minus 1, then the only thing you are left behind is x of n, is the present sample of the input sequence X of n. Okay, so this is X of n. So therefore you can formulate the description of an inverse system for an accumulator. So for this discrete time accumulator, if your W of n takes the difference between the present output and the immediate past output, the difference, this W of n, will correspond to X of n. So this was the sequence originally that we started with. So we were summing up all the samples from minus infinity to n, but if you take the difference between whatever the sum is at the present time index n and the sum that exists for one previous sample or one preceding sample at n minus 1 up until n minus 1. Okay, up until this sample, up until n minus 1. So you're left with the present sample x of n. So this is indeed the inverse of your accumulator. Okay, so the inverse exists, and this inverse, what it does is, whatever the operation that the system has done, whether it is a continuous time system, discrete time system, doesn't matter, whatever the transformation that these two systems are doing on the input signal, the inverse system, if it is invertible, if it is invertible, the inverse system exists, and this inverse system, when cascaded with the original system, produces an output that recovers the original input xt or xn. Okay, so this inverse system basically reverses whatever the operation or transformations has been performed by the original system. So if the system is invertible, then yes, the inverse system exists, and this inverse system reverses the transformations or operations that has been initially performed by the system. Okay, by the system. Okay, so thus you see the series interconnection in Figure 145a and an overall input-output relationship, which is the same as that for an identity system. So an example of an invertible system that we have seen in part B was you scale the input by twice, and then WT scales it back to you normalize the amplitude by multiplying it by one half, and then you are getting x of t. So that is what is being explained over here. So for example, if the system is scaling the input, the amplitude, then the inverse system is going to reverse this scaling factor of 2 by simply multiplication with 1 over 2, and you get WT, which is in fact equal to xt. Okay, that's the idea behind the inverse systems. So this example is illustrated in 145b over here. Okay, similarly, we have seen the example for the accumulator in 145c. So another example of an invertible system is an accumulator. It's a discrete time system. So for this system, the difference between two successive values of the output is precisely the last input value. So therefore, in this case, the inverse system is W of n is y of n minus y of n minus 1, and that gives you x of n. So this is indeed the inverse system. So accumulator is an invertible system. Okay, so you can still recover from it the original input at n discrete time index n present at the present index n by simply cascading with the accumulator the system W of n equal to y of n minus y of n minus 1. Okay, all you need for the input is the output y of n. That's it. So but remember that this the inverse and the system, they both are systems with memory. Okay, they are not memoryless systems because they require the information in the preceding samples of the output. Okay, similarly, this system in the accumulator requires all the information in all the samples of x of n from minus infinity to the present time index n. Therefore, both the systems they're coming with memory, right? So they require some registers for storage of the sample values. So this figure 145 is the concept of inverse systems. In A, you have a general invertible systems. Okay, so you have W of n equal to x of n, and then there's an invertible system example that is given for continuous time signal, and then you have invertible system for an accumulator in part C. So that is what is being shown. That is what is being shown over here. Okay. Then there are some examples of non-invertible systems. So for example, if you apply to a certain discrete time system an input x of n, and this difference equation is explaining is that irrespective of whatever is the input, the output y of n is always 0. Okay, so there is no way you can recover what the input was. I mean, it could have multiplied the whole of the sequence, whatever is this arbitrary sequence is, the output is 0. Okay, so whatever is the input sequence, the output is 0, and there is no way you can recover back your original sequence. Therefore, the system is non-invertible. So that is the system that produces a 0 output sequence for an input sequence. It's a non-invertible sequence. Similarly, there's another example for a continuous time system. Even if you see, you look at this, this is again a system that does not require memory. Okay, so to evaluate the present time instant t, the output at the present time instant t, you just need to square the input, okay, the amplitude of the input at that instant. So it's again a memory less system. However, it is non-invertible because even if you are going to, if you think that you can um, cascade with it a system that takes the square root to reverse this effect, it's not going to help, okay, because you cannot recover the sign. So you see the input that was being applied to the system, you had an xt, and then the transformation was such that well, this y of t, that the output that was being produced was the square of xt, okay, so basically you're squaring this up. So you cannot go on and take a square root because we don't know what sign to recover, plus or minus, so we cannot invert the system. So the system produces, so in the first case we have zero output sequence for any input sequence, then over here we don't know what the sign is, so this is again a non-invertible system. Okay. So the concept of invertibility is important in many contexts, and in communication systems, if you are familiar with them, one example arises in systems for encoding used in a wide variety of communication applications. So in such systems, a signal that we wish to transmit is first applied as an input to the system as an encoder. What encoder does is it encrypts the sequence so that the communication can be done over a secure channel, or it can be secured, or for private communication you can secure the transmitted data. So you see there are many reasons that you are going to encrypt your data, you're going to give your data to an encoder. So this range from the desire to encrypt the original message for secure private communication to the objective of providing some redundancy in the signal, okay. So you might, for example, add what is known as parity bits. So you might add some redundancy. You add more samples or bits to the sequence or the signal, and this in turns helps in recovering any errors, so that any errors that occur in the transmission channel, they can be detected and possibly corrected. So for example, the correction schemes for like forward error correction schemes, they might add some parity bits. So there's some redundancy in the original transmitted signal. So whatever impairments the signal is going to suffer on the transmission channel, they can be corrected later on by the decoder. Okay. So for lossless coding, the input to the encoder must be exactly recoverable from the output. Okay. So it means the encoder must be invertible. Otherwise, I mean, on the decoder side, so whatever you are transmitting, so for example, let's say you have a transmission over here, you have a transmitter or a modulator in the transmission system. So you are giving it some message signal, call it m of t. This has some information in it, and then this signal is supposed to be traveling on a channel. The channel could be of some dispersive nature, which might add some phase noise, or which might, in other words, it might grab all the frequencies if it is a white Gaussian noise. So what happens at the decoder side or the receiver side is we have to recover the message signal intact, the original message signal. So if the system is not invertible, there's no way you can have m of t. So an encoder must be an invertible system. In other words, the transmitter over here must be invertible with the errors that channel is going to introduce in the transmitter signal. So at the end, if you want an MT, an exact copy of what was transmitted, the receiver is supposed to be an inverse system. That means the transmitter system should be an invertible system, okay, so that all the errors or dispersions created by the channel could be recovered. The message signal can be recovered from all the errors, and you have the original message signal intact at the receiver side. Okay.